Hello, students. I had a question come in about the fundamental theorem of arithmetic and kind of how we might use that. So I'll just kind of say, just a quick reminder, fundamental theorem of arithmetic is a way that says if you have a composite number, you can write it as a product of primes in exactly one way, as long as you kind of keep the order of the primes the same. It's the idea of two people factoring into primes, but doing it in a different way. So what this is really saying is that the number 260 can be written as 2 times 13 times 2 times 5, and that you will not be able to get a different grouping of primes unless you just change the order of these. So if you left it as 2 times 2 times 5 times 13, or potentially as 2 squared times 5 times 13, all of those get you to 260. And if you put a different prime number in or a different quantity of these primes in, you're not going to get the same answer back out. So this is the uniqueness, the one and only one way to do it. So what good is a theorem like that? Well, what's great about it is it says that for you and your students, no matter what you do with prime factorization, if you prime factor and a different person prime factors, it means we're going to end up with the same results. So what that can look like is something like this: 2 cubed times 5 to the 7th times 11 squared, let's say. And over here, somebody else has their number is 2 times 5 to the 7 times 11 times something, and we just don't know what that other something is. Well, you can then go through and kind of compare. On the left-hand side, these are the exact primes, and it has to equal what's on the right-hand side. So you could kind of compare. Here's a 2. There's only one of them. Over here, my other number had 3 of them, but there's an equal sign between them. They have to be the same. Fundamental theorem of arithmetic says, hey, you better have a couple more 2's in that magic box over there so that we end up with 2 cubed. And let's see here, 5 to the 7, 5 to the 7. So those match up. So I don't need anything extra here. And I couldn't put another extra 5 because there are only 7 total. And lastly, I have 11 squared. On the right-hand side, I have 11 to the first. Again, they have to match. So that means I have to have another 11 in there so that 11 times 11 becomes 11 squared. So if you were trying to show with this fundamental theorem of arithmetic that these two are the same, if anyone was missing some quantities, you could actually figure out exactly what those quantities would have to be. Right. And what else? Maybe some other sample problems. Let's see. So if we had something like a 2 to some power times 3 to different power perhaps is equal to 6 to some exponent up here, I'll call it z. Could you find values for these that would make this equation true? So let's see here. Yeah, let's just say we had a 2 to the 5th, right? Well, what we would know is I need to have at least 5 2's on the right-hand side, so that means this one has to have a 5, because 6 is really 2 times 3. But that means then, in order for this to be equal, then my exponent on 3 had to be 5 as well. So yeah, if you have a base of 2, a base of 3, can we raise those to powers to get some kind of base of 6? And the answer is yes, you can. And there's many, many different ways to do it. All right. Yeah, I think that's probably the biggest piece there for that theorem. Let me clear this out of the way and see if there's any other theorems there that might be kind of on the way. So that's the fundamental theorem of arithmetic. You can factor different a strategy for factoring that I use, but the values we get, the primes and composites that we end up with should match perfectly. Number of divisors. I mean, this is okay. It's not a huge one, honestly, just because it's basically saying if you have a divisor, you get another divisor for free. But it doesn't fix what we saw in class today. It doesn't fix the idea of what do we do if the one that we end up splitting it turns out to be the same. So if you have a divisor of a number, let's just say the number is 36. This said 24. I'll do 36. Then let's see here. I know that 3 does divide 36. And this theorem says, okay, now take 36 and divide by 3, and you get 12. And all it is saying is that, let's see here. All it is saying is if you know that you get this, then 12 has to divide 36 as well. Which makes sense because 36 then would be equal to 3 times 12. And this would say 3 divides 36. It also says 12 divides 36. So you just pick up a free divisor along the way. Here's the exponents we kind of talked about in class. Let's see here. Yeah, this is the one where we would kind of say, hey, I need all of those things to divide. So we'd add 1 to the exponent. That would get us there. Determining whether a number is prime, we use that prime squared piece, which means we kind of undo it typically. So we'd be taking the square root just to kind of make things a little bit quicker. And yeah, basically it says theorem 415 is equivalent to this one. So 416, 415 are exactly the same. If you want to know, like 397, is it composite or prime? I would take the square root, and then I would check all the primes up to that square root. And yep. Yeah, so this is similar to the sieve that we did in class. The wording here might be even a little bit better. Like once you circle 2, in this case, we shaded them orange. Once you shade it in orange, the first number you do not cross out that 2 does divide is 4. And I even gave the explanation verbally in class. I said, remember, think about multiples of 2 or multiples of 5 that you already got. You've already got 5 times 1. You've already crossed off 2 times 5. You've already crossed off 3 times 5. You already crossed off 4 times 5. What you might not have crossed off yet and should not have crossed off is 5 times 5. So 25. Yeah, I don't see anything else here on the theorem wise, so I'm going to call it good from here. Hopefully that helps. And let me know if you have other questions or if you want to jump in. Maybe there are some questions. A back and forth is just fine. You can choose if you want to have that recorded or not. You can post it for everyone or just for you. Totally up to you. Let me know how I can support you, and I hope you have a great weekend. All right, off you go.